This is activity 2, Race to the Bumper Cars, from lesson 12, using graphs to compare relationships. And this is a continuation of Tyler's walk, which was an activity from lesson 11. And in this case, there are 3 friends of Tyler's that are also moving from the ticket booth to the bumper cars, and they move at different speeds. And so we're going to look at each one of these in detail, draw a graph, and look at the relationship of one to another, who's moving the fastest, etc. All right, but first remember that it's 50 meters from the ticket booth to the bumper cars. So it takes Diego 30 seconds to move that 50 meters. It takes Lynn 20 seconds to move that 50 meters. And it takes May 40 seconds to move that 50 meters. So in Diego's case, Diego jogged. So he's moving faster than a walk. And let's assume that his jog is faster than Tyler's walk. So he's going to get there sooner. It's going to take him less time to get to the bumper cars. And he's moving at a steady pace. And he's starting from the bumper cars. He's starting right at 0. In 30 seconds, he moves 50 meters to the bumper cars. So you can figure that out, that if it took him 30 seconds to move the whole distance, then half that time, 15 seconds, he will have moved half the distance. It's 25 meters. And the constant of proportionality, remember, is the y value divided by the x value. And so we can look at it just as this row right here. It's 50 divided by 30, which is the same as 5/3. So it's 5/3 meters per second. Now remember, 5 meters per 3 seconds is the same as 5/3 meters per 1 second. So get used to looking at this fraction as a value per 1 second, or looking at the numerator as, in this case, the distance, and the denominator as the time. So 5 meters per 3 seconds. So you're going to get used to going back and forth between those two different ways to look at this number. And if we use 25 over 15, we would still end up at 5/3 meters per second. All right, now Lynn ran to the, Lynn is a she. Every once in a while I wonder about that. So she ran. So Lynn ran at a steady pace to the bumper cars. So let's assume that Lynn's running is faster than Diego's jogging. She left at the same time as Tyler, Diego did as well. She ran at a steady pace, and it took her 20 seconds. Now they're going to give you her distance in this case. Over here they gave you Diego's time, and you either use the scale factor or the constant of proportionality to figure out his distance. So remember, 15 times this constant of proportionality, 5/3. 15 times 5/3 is going to give you 25. 15 divided by 3 is 5. 5 times 5 is 25. So you can use either the constant of proportionality, which you get from this row, or scaling. You can do the same thing here. So if it took Lynn 20 seconds to move that 50 meters, then half that distance, 25 meters, it will only have taken her 10 seconds. And she left at 0, so 0 seconds, 0 distance. And finally down here, this is the constant of proportionality. So you take the y value and you divide it by the x value. In this case, it's 50 divided by 20, or 50 20ths. Divide each of those by 10, so you end up with 5/2. So that's 5/2 meters per 1 second, or 5 meters per 2 seconds. So here's, say this is 5 meters in 3 seconds, 5 meters in 2 seconds. So Lynn is moving faster. So you can use this constant of proportionality. Now look what you do. You use the reciprocal, or the multiplicative inverse, to go the other way. So if it's 20 times 5/2 equals 50, then it's 50 times 2/5. It's 2/5 of 50 to equal 20. So 2/5 is the multiplicative inverse of the constant of proportionality, or of 5/2. So 25 times 2/5, 2/5 of 25, same thing. So 25 divided by 5 is 5. 2 times 5 equals this 10. And that makes sense. It's half the time to go half the different distance. But I want to use the multiplicative inverse of the constant of proportionality to figure that out. I want to get used to doing that. A lot easier done than said, believe me. So in 0 time, she moved 0 meters. So 0 seconds, 0 meters. And May jogged. So that's slower than Lynn running. We don't know if she jogged at the same rate as Diego. We'll figure that out in a little while. But May jogged, but she, a little bit different. She delayed leaving the ticket booth. Maybe she wanted to get a drink of water or a snack, something. For some reason, she didn't leave right at 0 time. She left 10 seconds later. So May left the booth 10 seconds later than Tyler. So they all bought their tickets at the same time. May hung out for 10 seconds for whatever reason and then left. So at 10 seconds, she's moved 0 meters. And then in 30 seconds, she moved 40 meters. So that is 30 seconds. It took her to move she moved in 30 seconds. At 40 seconds, she moved 50 meters. So it took her 30 seconds to move this 50 meters. So half of that 30 seconds is 15 seconds. But remember, she delayed 10 seconds. So right here, this is going to be 25 seconds. It's 10 seconds that she finally started. And then in 15 seconds, she moved half the distance, which is 25 meters. So that 10 plus 15 is equal to 25 seconds. So it took her 25 seconds to move 25 meters because she delayed 10 seconds in starting to move to the bumper cars. All right, so 40 seconds, she moved the 50 meters. And is there a constant of proportionality? At 1 second, she has moved 0 meters. She didn't move until she got to 10 seconds or after 10 seconds. So 1 second, she moved 0 meters. So is there a constant of proportionality? And the answer to that is no, there's not. 0 divided by 10 is 0. 25 divided by 25 is 1. 50 divided by 40, or 50 40ths, is the same as 5/4. And 0 divided by 1 is 0. So it's not a proportional relationship. There is no constant of proportionality. So this presents a little bit of a different issue when we graph this and think about this. This is Tyler's walk. And remember, he was walking, and it took him 40 seconds to move that 50 meters. So Tyler was walking, Diego jogged, Lynn ran, and May jogged. So now let's put all of these on a graph. And you really only need 2 points to graph these. First of all, remember that the bumper cars are 50 meters away. So this is elapsed time. So after they bought, the time after they purchased their tickets. So how much time went by after they purchased their tickets as they moved to the bumper cars. Now the bumper cars are 50 meters away. So the y-axis is distance from the ticket booth in meters. Bumper cars are 50 meters away. And I put all 4 graphs here so we can treat this as a little puzzle to figure out who's who as we go through this. And you're going to see one person delayed leaving the ticket booth by 10 seconds, so we know who that is. And what's the difference in each of these is their slant. Each of them leave the ticket booth at the same time, but they're moving at different speeds or different rates to move to the bumper cars, which are 50 meters away. So the first one, 50 meters in 20 seconds. So right here, this person made it to the bumper cars in 20 seconds. And this person ran. So it only took them 20 seconds to get to the bumper cars. I'm going to talk about this in a few moments. This is 2 seconds. So it's 5 meters in 2 seconds is the same as 50 meters in 20 seconds. This is just multiplied by 10. All right, this person jogged, and it took this person 30 seconds to make it to the bumper cars. So they ran a little bit slower. This person ran, this person jogged. So 50 meters. So imagine it took 20 seconds for this person and took 10 seconds longer for this person to get there. So this person's moving slower, at a slower speed than this person. There is this person who left. This person also jogged. They left 10 seconds later, so it's not proportional. But notice it's the same slant as this person who also jogged. So they are actually jogging at the same rate. They are moving over this distance of 50 meters at the same speed once this person starts. So you can imagine this person started, and then this person started 10 seconds later, is jogging at the same rate. So this person reaches the bumper cars in 30 seconds, and then another 10 seconds goes by, and this person reaches the bumper cars, even though they ran at the same, or they jogged at the same rate. And finally, this person walked, and it took this person the longest to get to the bumper cars, although notice that they got to the bumper cars at the same time as this person right here. And let's just zoom in on this for a second. So one person covered 5 meters in 2 seconds. So that's the fastest. It's the steepest slant. This person covered the 5 meters in 3 seconds. And this person covered the same 5 meters in 4 seconds. So the 4 seconds is the slowest, the 3 seconds is the next, and the 2 seconds is the fastest. All right, so let's put a name to each one of these and add a little bit more detail. So Lynn moved at 5/2 meters per second. So this is Lynn right here. 5/2 meters per second, or 5 meters per 2 seconds. So in 1 second, we went up to Lynn's line, it would be at 5/2 meters. We're going to actually look at that in a little bit more detail in a moment. So Lynn ran. Diego jogged, and he jogged at a slower speed than what Lynn ran at. So 5/3 meters per second. Now I'll hold on for that. So Diego jogged. So that's 50 meters in 30 seconds, which is the same as 5/3 meters per second, or 5 meters in 3 seconds right here. And Tyler walked. So he walked at a speed of 50 meters in 40 seconds, per 40 seconds. So that's 5/4 meters per second, or 5 meters in 4 seconds. Same thing, 5/4 meters per second, or 5 meters per 4 seconds. And finally, May, we don't know her, it's not a proportional relationship. So what is her speed? We can state what her average speed was. Her average speed was the same as Tyler's, 5/4 meters per second, because it took her the same 40 seconds to get to the bumper cars. So you can imagine that Tyler left early and May started jogging, and as she was jogging, she eventually caught up to Tyler right at the bumper cars. So her average speed is 5/4 meters per second, but it's not proportional. She didn't start running right at 0 time, or jogging right at 0 time. She delayed it by 10 seconds. So she has an average speed of 5/4 meters per second, whereas Tyler has also has a speed of 5/4 meters per second, but his speed is proportional to the time it took him. All right, so it's a little bit hard. It might be a little bit hard if you're not used to looking at the fractions to tell which is slower and which is faster. If you change each of these fractions to a mixed number, it becomes a little bit easier to look at. So 5/2 is the same as 2.5 meters per second. I'm going to draw you a picture of that in just a moment, but this is the largest distance in 1 second. Diego is 1 2/3 meters per second, and Tyler is 1 1/4 meters per second. So 2.5 meters is 4/2 is that 2 meters, and then another 1/2 meter is the 5/2. So this is 2 1/2. This is 1 2/3. So 1 meter is 3/3. And then another 2/3 gets you to the 5/3. So this is 1 2/3. And 1 meter is 4/4. And then another 1/4 gets you to 5/4 for Tyler. So this is 1 1/4, or the same as 5/4. So a drawing of this, Lynn is the farthest. So she traveled the farthest in 1 second. It's the steepest graph. So she's traveling the fastest. She's getting there the fastest, covering this 50 meters sooner, 20 seconds, than the other people. So 5 halves, that's the same as 5 times 1/2. Well, this is 1/2, and it's 5 of those halves. So you just multiply this by 5, and you're going to get Lynn's distance. I'm going to show you that in just a moment. This is 1/3, but Diego ran 5 of those 1/3. So 5/3, or 5 1/3. And Tyler ran 5 1/4. 5/4, or 5 1/4. So this length times 5 is going to give you Tyler's run. So Lynn is 5 1/2, or 5 halves meters per second. So she's out to here. Diego is 5 1/3, or 5/3 per second. So he is at this point. Here's 3/3 right here. 1 2 3/3, 4 5/3. So this is 1 2/3. And Tyler is at 5/4 meters per second. So he's only to here in 1 second. So this is 1/4, 2/4, 3/4, 4/4. And then 5 of those is going to get you this extra 1/4. So it's 1 1/4. So Lynn's the fastest. She covers the farthest distance in the same amount of time as everybody else.